You have my voice? In the program we see this proposition and we see this example. We express this proposition, let G be a semi-topological group and A belong to G. The following functions from G to G are called the right and left translations by this notation, are homeomorphism. Let me recall this definition for you. In general, a function such as t from G1 to G2 is called a homomorphism. G1 and G2 are two groups, okay? Then T is called homomorphism if we have these three conditions. T is bijective. T is one-to-one and onto. T is continuous and the inverse of T is continuous too. The inverse of T is continuous too, okay? Now if T from G to G is a homomorphism, we say T is an automorphism. If G1 and G2 is the same, okay, we call it this homomorphism and automorphism. Sorry, this is homeomorphism. Not homomorphism. Homeomorphism, okay? Homeomorphism. Now in this proposition, we consider these functions Ra, okay? Ra is this function. Let me write for you. For any x in G, Ra of x equal to x A, okay? X A. Or if we consider G and if we consider G and A star, G and A star, okay? If we consider this as binary operation, A from G to G is this function, Ra of x equal to x A star A. For simply, we write this xa, okay? And also La from G to G is this function LA of X equal to A star X, or simply AX. Okay, or simply AX. Now in this proposition we prove that these two functions are homeomorphism. Please note that RA from G to G by this function root X maps to XA, and LA from G to G by this function root X maps to AX. We want to prove that these two functions are homeomorphism. So that we must check these three properties. These three properties for this function from G to G. For the first condition, we must prove that this function is one-to-one and also onto. RA is one-to-one because if for two elements x1 and x2 in G, we have this equality, RA of x1 equal to RA of x2, then by the role of these functions, this equal to x1a, okay, and this equal to x2a, so that x1a equal to x2a. This implies that these two are equivalent because we can act the inverse of A from the right side of this equality, okay? It is very trivial. It is very trivial because if we have this, for example, x1a x1a equal to x2a, then x1a multiplied by the inverse of A equal to x2a multiplied by the inverse of A. And we know that the binary operation in groups is associative, so that is equal to this, and the second equal to this element, but is equal to identity, so that is equal to x1e and the second equal to x2e, and e is the identity element, so that this is x1 and the second equal to x2, so that because we know that this is RA of x1 and this is RA of x2. We prove that if we have this equality, then we have x1 must be equal to x2, and this shows that RA is 1 to 1, okay, 1 to 1. Also, this function is onto because for any y in G, we can consider this element in G this is an element of G, and we have this equality array of this element equal to this element multiplied by A, and this is identity element, so that this is equal to Y. Simply we prove this for any, we prove this for this function array from G to G for any y in G. We found an element such as x in G such that array of x equal to y, and this shows that array is onto, okay, this x equal to this, okay, but we have an element by this property, so that this function is onto, and this shows that this function is one-to-one and also onto. So we have this property, this T, this function is one-to-one and onto, is bijective. Now we must prove that T is continuous, and the inverse of T is continuous too. Since G is a semi-topological group, for each A in G, these two functions are continuous. Because if we consider a star or G, or simply, please, G is the binary operation of G, okay? The binary operation. Then we see that GA equal to LA, and GA equal to L. In these two functions, consider this notations that we used in the previous session. These notations, okay? Let me, okay. For any x0 in x, gx0 and gy0, down and up. Gx0 for any y equal to this, and gy0 equal to x star y0, so that ga of x equal to x star a star x or ax, okay, and also ga of x equal to x a. By this notation, we see that we have these two equalities, but we know that the binary operation on G is separately continuous. These two functions are continuous by the definition of semi-topological groups. I write this again for you. GA of x equal to this or this, and this equal to LA of x, and GA of x equal to XA, and XA equal to LA of x. So that these two are continuous because G is a semi-topological group. And this shows that we have this condition, this function is continuous. Now we must prove that the inverse of this function is continuous too. The inverse of this function is continuous too. For this, we see that the inverse of this function equal to this translation. And we know that this is the continuous function because this is an element of G. Okay, this is an element of G. This is an element of G. This belongs to G. We know that L of x is continuous for any x in G. And this equality hold easily because if we consider this composition LA composition but L the inverse of A for any x is equal to LA of x star the inverse of A, and this equal to this multiplied by A, and by associativity this equal to this, and this equal to x because this is the identity. Okay, and this is I of x. I is the identity map. Okay, I is the identity map. So that the composition of these two functions is identity. So that this is the inverse of this function, and this is the inverse of this function. Please note that you know that if t is a function from x to y and s is a function from y to x, s equal to the inverse of t if and only if SOT equal to the identity map and TOS equal to the identity map. Okay, in this proposition we see that the composition of these two is identity and the composition of these two is the identity, so that this is the inverse of this function, and you prove this equality. So for this function we see that this function is bijective, continuous, and the inverse of this function is continuous too. Similarly, for LA from G to G, we can prove that LA is bijective or LA is 1-to-1 and onto LA is continuous and the inverse of LA is continuous too. So that LA is a homeomorphism. Okay, and this condition holds because you can prove easily that this equal to this, similar to RA. Okay, we have this equality too, so that for any for each A in G, these two functions are homeomorphism. Okay, these two functions is called translation, right translation and left translation. Okay, right translation and left translation. So that in this position we see that right and left translation by this function rules are homeomorphism, that we see the proof of this proposition. Dear students, do you have my voice? Dear students, do you have my voice? Mr. Sajjad, Mr. Ghassan, do you have my voice? Okay, and hello, Hashtag Dalil. Do you understand the proof of this proposition? It is clear or not? Okay, very good. Thank you, Sajjad. So, for each A, right translation by A and left translation by A, both are homeomorphism. For any semi-topological group, G must be a semi-topological group. When we have this corollary, if G be a semi-topological group and F be a closed in G, U be an open subset of G and A any subset arbitrary, then for any A in G, these subsets of G are closed, FA and AF. Are closed, and these subsets are open. These subsets are open. And this is very nice corollary of the previous proposition. And the proof of this proposition is very easy. For the proof, let F be a closed subset of G. Then, for each A, we consider G a semi-topological group. For this part, we need only semi-topological group, not topological group. Oh, okay? And F is closed. We must prove that this AF and FA is closed too. For this, we know that this translation is continuous. We proved this in the previous proposition, and also this is a continuous function. And we know that in any topological spaces, a function such as t from x to y, these two are topological spaces, is continuous if and only if this equal to for any open subset of y the inverse image of u is an open subset of x, and this equal to for any open subset of closed subset of y the inverse image of f is a closed subset of x. These are equivalent, okay? This equal to this, and this is equal to this statement. Now, if we consider for example this function from G to G, this is continuous because this is a left translation. Okay, continuous. So that for any closed subset of G, the inverse image of this function of f must be closed in G again. Closed, okay? If we consider t, this as our function t, okay? The inverse image of f, this is our t. But we prove that this inverse image equal to fa. We prove that this inverse image of f equal to fa, so that this must be closed. This must be closed, and we prove this in this equality. This is very easy because the inverse image of this set equal to the set of all x such that t of x belong to f. You know that x is an element of this inverse image if and only if t of x belong to f, okay? T of x, so that x belong to, for example, this array, okay? This inverse if and only if array1 of x belong to f, and this is hold if and only if this belong to f, okay? That we write this for u, this belong to f, and this set equal to this set, the set of all x such that x belong to fa. We prove this for you in a star. This belong to f equal to, there exists an element of f such that x a minus 1 equal to f, so that x equal to fa. You can act a from the right of both sides of this equality, so that x equal to fa, and fa is an element of fa, f, capital F, okay? So that these two are equivalent, and this is fa, okay? Equal to the set of all fa such that f belong to f. And since we know that this is a closed subset of G, this is closed too. And similarly, this inverse image for left translations equal to AF. So that AF is closed, because we know that this is closed. So that AF is closed. And as another proof, please note that this is very, very important, that it is very important that T from G, from X to Y, okay, from X to Y, let T is bijective, okay, then we have the following are equivalent. 1, 2, and 3. One, T is continuous. 2, or the inverse of T. T is open, and 3, T is closed. These 3 statements are equivalent. Please note that T is open, have these definitions. If U be an open subset of X, then T of U is an open subset of Y. And the definition of closed function is this: if f be closed in X, then T of f is closed in Y. Okay, closed in Y. Now for the proving, we know that RA is homeomorphism. Okay, so RA is bijective, and the inverse of this function is continuous. So RA from G to G is open, and also is closed. So array of f is closed. This function is closed, so that any closed set must map to a closed set. This shows that fa is closed because array of f equal to fa. And similarly, LA is closed so that LA of f is closed, but LA of f equal to AF, so that these two must be closed. And this is another proof for this part. Okay. So that we prove this proposition or this proposition, FA and AF are closed. And these sets are open because since LA and LA are homeomorphic, these two functions, these two are bijective and have continuous inverse. Okay, so these two functions are open functions. Open functions. Therefore, since U is open, you consider an open. Okay, please note that U is an open subset, so that array of U is open and LA of U is open, but array of U equal to UA and LA of U equal to AU, so that UA and AU must be open. It is very clear. Please note that, for example, array of U equal to the set of all array of X such that X belong to U, and this is equal to A X, the set of all XA such that X belong to U, and this is equal to UA, and similarly LA of U equal to the set of all LAX such that X belong to U, and this is equal to AX such that X belongs to U, and this is equal to AU. So that these two are open. But these two are open again. This is very nice. Please note that AU equal to the union of all AU such that A belongs to A. Okay? And UA equal to the union of all UA is all U. A belongs to A. No, we know that all of these are open set, so that this union must be open. We know that any arbitrary union of open sets is an open set. Any arbitrary union of open sets is an open set. Since we know that these two are open set, its union must be open, okay? And this union must be open. And we have this corollary. That is very, very important corollary. And also we have this corollary, let G be a semi-topological group and X1, X2 belong to G. Then there exists a homomorphism F such that F of X1 equal to X2. This is very easy because we can consider this homeomorphism. We know that this is an homeomorphism. If we consider F equal to this, F of X1 equal to F of X1 equal to if we consider F equal to L X1 X2, then F of X1 equal to L X1 inverse X2 of X1, and this is equal to X1 inverse X2, and we know that this is equal to identity element, so that is equal to X2. So F of X1 equal to X2, and we have this property. Okay, this is enough for this session and for this section. We will continue in the next session, inshallah, with this chapter, topological group. Topological groups. It is not that dear students, do you have my voice? In topological group, we have these two facts Let G be a topological group. The following statements are equivalent. G is T0, G is T1, and G is Hausdorff. In topological group, these three are equivalent. We know that this three condition is not equivalence in general, but in topological group, these three conditions are equivalent. Okay? And we have this theorem. These translations are homeomorphism. We prove this in semi-topological groups. Please note that I write this for you. Please note that any topological group is a semi-topological group. Any topological group is a semi-topological group. Equivalently, if the binary operation is jointly continuous, this is separately continuous. So that in this proposition, since G is topological group, G is semi-topological group, and we prove this statement for semi-topological groups. So we must prove these three statements, and these two are very easy. For example, for the inverse map, this function, if we consider h from G to G by this function, x maps to the inverse of x, this h is homeomorphism. This function is continuous by the definition of topological group. In any topological group, inverse map is continuous. And also, HOH is identity. If we composite this function with itself, we see that this is identity map, so that the inverse of H equal to H, and H is 1 to 1 and onto, which is bijective. Okay, this is 1 to 1 and onto, so that, and the inverse of H equal to itself, so that H is continuous and the inverse of H is continuous and H is bijective, so that this is a homeomorphism, so that we have this condition 2. And finally, if we consider a function from G to G by this function rules, K of x equal to A is A inverse. This is homeomorphism again, because K equal to this composition of LA and RA inverse. And this is very easy that we write this for you. For any x, this composition of x equal to this and this equal to K of x. This is very, very trivial. Please note that the composition of two homeomorphism is a homeomorphism, and this is very easy. Since we know that these two are homeomorphism, its composition must be homeomorphism. And we have this proposition similar to semi-topological groups. Okay? Similar to semi-topological group, we have this corollary. And we can finish this chapter for you. It is enough for you. Dear students, do you have any questions? Okay, please have a break for 10 minutes and we will continue after. Yes, I sent for you some offline file and some booklet, okay? You can upload from this software. Let me write for you. And
أقوم بتحميل الملفات في هذا النظام. استرح لمدة 10 دقائق ثم ابدأ الفصل التالي.
okay, we will continue after 10 minutes. Okay, thank you very much.